What is up guys, welcome back to this series on ROS2 based navigation. In the previous video, we started a Nav2 based project in ROS2 where we were building a patrolling robot that would move between 4 points in your simulation in Gazebo. The simulation looked like this, and this is the design we discussed in the previous video. We said that the first half, which we already developed in the previous video, would be infrastructure, so to speak. That included your Gazebo setup and your Nav2 setup inside our own custom package called tb3_sim. Once again, that package had your tb3 simulation launch, RWiz launch, Nav2 launch, and AMCL init pose. If you don't know what I'm talking about, please look at the previous video to understand how we started building this project for a patrolling robot in ROS2 and what we're doing in this video. But in this video, we complete this project with the second half. We build our application package in C++. This package will be called tb3_autonomy, and it will be responsible for sending Nav2 goals to Nav2 running, and Nav2 will then in turn ask tb3 Gazebo using command velocity values to move the robot to whatever location we want. The first part, which is tb3_sim package, is already ready, right? Because we did that in the previous video. In this video, let's start looking at our application C++ package and build it from scratch. But before that, let's also recap what this design actually means. I already told you about these two components. One would be your infrastructure, the other one would be the application C++ package we build now. If you think about it, tb3 Gazebo is your component which is effectively your world and your robot in simulation. Nav2 is your Nav2 framework running with multiple packages, and C++ application package is actually the place where we compute everything. If you look at a real project, your tb3 Gazebo will be replaced by a real robot, but application C++ package is something we can use irrespective of us working in simulation or in the real world. Of course, you'll need a lot more tuning because the real world is very different from simulation, but in this application C++ package, you will compute whatever you want and you would decide where the robot should go. For instance, if you also have vision components in your system, your C++ application package will also decide where the robot should go based on the vision component of things. So where you find the object is where the robot should go, and then it'll give nav goal to nav2. Now, before we build this package, let's look at what the structure of this package is. This is what your package looks like. You will have your ROS2 autonomy node, and inside it, you will have a behavior tree controlling node. In the previous video, I already told you that we will use a behavior tree to control this robot. Now, first of all, let's talk about this autonomy node. In ROS or ROS2, you have your nodes that usually act as a wrapper over your core functionalities. Since ROS or ROS2 is a middleware, the idea is to enable inter-process communication. In this case, C++ application package is one process. And to enable this communication, you have messages, services, actions, etc. So in this example, your core functionality will be in your behavior tree, and your ROS2 node will act as a wrapper so that you can have all communication between your core functionality and whatever other module. In this case, Nav2 is the other module we are talking to. In general, if you think about this design, this also applies to whatever system you're building in ROS or ROS2. You usually want to set up your node even in code in such a way that it only acts as a wrapper, and your core functionality should not be mixed up with setting up your node and all the interfaces between different nodes. Now, as I discussed before, we have a behavior tree to control the robot, and the robot is supposed to move between 4 points continuously. Let's look at this behavior tree in detail then. This is the behavior tree we're looking at. It'll have a sequence node and then 4 action nodes. Each node is responsible for moving the robot to one specific location, and we'll have 4 locations. We will decide these 4 points using a configuration file, and then each node will move the robot to that specific location. So again, sequence node with 4 action nodes. Now, how do you create this behavior tree? Using behavior-tree.cpp library. If you don't know about behavior trees or behavior-tree.cpp, I have a series on that on my channel. Please check it out. Here we have one sequence node and 4 action nodes. So what should we do? We can create 4 different classes for 4 different nodes based on these locations. So 4 locations, 4 nodes, but that actually makes no sense. Instead, since the functionality is the same across all these action nodes, we will create one class and reuse it for 4 of these nodes. And to this class or to this node when it's running, we will send the location using the port. These are behavior tree or behavior-tree.cpp concepts. So I have that covered in my series on behavior tree. So as I said, we'll have only one class and we'll create 4 nodes, and all of these nodes will take the location of the robot as the input using the input port, and it'll ask the robot to move to a different location based on the input it got from the input port. Now let's look at the structure of this tb3_autonomy package we will create. The first one is an include. Since we are creating a C++ package, you will have all the headers you create for your own code. src is where the definition of your core functionality resides. Launch is where you'll create a launch file. bt_xml is where you will create the XML file for your behavior tree. That's the behavior tree I just showed you now. Config is where you will create your configuration YAML file, which will have these 4 locations where the robot should go. And I'm sure you know about cmakelist.txt and package.xml when it comes to a ROS2 package. But if you're not clear about what I just discussed, don't worry about it. As we build this package, things will be more and more clear and you'll understand everything in a bit. So let's first look at where we are and what we already had from the previous video, and then continue and build this package called tb3_autonomy. So this is what we had. We had our infrastructure with your tb3 gazebo launch files, your ROS launch files, Nav2 launch files, and AMCL init pose, as I said before. In the previous video, we completed setting up our infrastructure with tb3 gazebo and Nav2. So when all of that was done, your robot was present in a world and you were able to move the robot using your ROS. So no intelligent computation package or any application package was present. Once the world was up, the robot was up, your Nav2 was running, and your AMCL init pose was done, you were able to move the robot using ROS GUI, but not from code. So that is what we're doing right now with the application package. Now that things are clear, let's start building our application package. This is my TurtleBot 3 workspace from the previous video. If you look at it, you have tb3_sim, which is the package we created. It was a custom package to set up the infrastructure I was talking about. The other two directories host all the TurtleBot 3 packages we needed. That is something we got from VCS tool. So let's start building our package here. We open up a new terminal, and in SRC, we create a new C++ package called tb3_autonomy. This is what we do for that. The package name is tb3_autonomy. In dependencies, I right now only have RCL CPP, which is ROS client library for CPP. We will have more dependencies in this package, of course, but I will add them in cmakelists and package.xml when we are actually building everything. So let's first create this package. Okay, we have our tb3_autonomy package. Let's go to VS Code. Okay, this is VS Code and we see tb3_autonomy package here. To start making this package, we start with the node. The node will have .h and .cpp files. Let's create a .h file first. Let's name this file autonomy_node.h. So this right now is inside your include directory, not inside tb3_autonomy inside include. Let's also create our cpp file for this. Let's go to a header file. Here, let's make a boilerplate node first. Let's call it autonomy node. Let's create a constructor here. So this is your constructor. You should know why we need this. If you don't understand what I'm doing here, please check out official ROS2 documentation for creating C++ nodes. Now this is your boilerplate, but as I said before, we will create a node that is a wrapper around your behavior tree functionality. What does that mean? That means we need to create a behavior tree here. So I've created a private member, which will be your behavior tree. To use your behavior tree from behavior_tree.cpp library, you need to have your include for that. In this video, I'm using behavior tree CPP version 3. I know version 4 is out, but I'm using 3 right now. If you're using version 4 because you're watching this video from the future, then you have to make some minor changes. But once you've watched this video and you know about behavior_tree.cpp library, you'd be able to easily do that on your own. Okay, so this is just a declaration, but when you have your tree, you also need to create a tree and tick the tree. So for that, let's create methods. We need to tick the tree periodically, so let's also have a timer to do that. This timer will tick the tree as per the frequency we set. Let's also have a method called setup that will initialize everything. Okay, so you have the declaration of your autonomy node ready. Let's go to the CPP file and write the definitions for all of this. We need to include the header file first. Now let's start with the constructor. In the constructor, let's just use a RCL CPP info statement. That's for initialization done. Now let's create boilerplate for all other methods we had in our header file. This was for setup. This would create your behavior tree and this would update your behavior tree. To run a node, we also need to have main, right? This is your main. Let's create our ROS2 node here. This is to initialize your context. This will create your autonomy node. And this is for spinning the node and then shutting down the context. Okay, so we have a boilerplate code ready for our ROS2 node, which is called autonomy node. What's the core functionality? Essentially, we want to create a behavior tree that is ticked at a certain frequency, and the behavior tree is responsible for moving the robot to location 1, then 2, then 3, then 4, and then back to 1, and this process keeps repeating. So before creating the behavior tree, let's make a method that actually can tick the behavior tree. We will use the method update behavior tree, which will tick the behavior tree again and again. So if I write comments for all of these, initial BT setup, create BT. So these are the functionalities. Now let's start with setup, which will be responsible for creating your timer that will in turn tick the behavior tree periodically. To take the behavior tree periodically, we first need a behavior tree. So the first thing in setup is to create your behavior tree. We already have a method for that. Now the next thing is to create a timer. Let's set the time period to 500 milliseconds. Milliseconds will be a part of your chronoliterals. Now we have the declaration of our timer in our header file. Let's create the timer. So this is your timer with your time period, and we bind this method update behavior tree for this object here. As soon as the node is created, you need to run setup so that your behavior tree is created and this timer is set up. So after creating the node, let's call setup. Setup is called once after you create your node. Now we want to create our behavior tree and then update the behavior tree periodically using the timer. But to create the behavior tree, we need to have our declaration and definition for your behavior tree, right? That is the core functionality. So let's create our behavior tree now. Let's call the file navigation_behaviors. So header file for that and a CPP file for that. Let's go to a header file and code up all declaration. The first thing we do is include behavior tree library. Now let's create the class for the node. The node is called goToPose, and we'll have 4 instances of this when it is actually running. But let's call the class goToPose. That will be an action node. Now you see that I've used stateful action node. That is an asynchronous node. In the series I made on behavior trees, I was using synchronous nodes. We don't necessarily need asynchronous in this example, but asynchronous nodes are used when you don't want your tick to block until the node sends back a success or a failure, but you want to do something else in between. So let's say you tick a node, but in code you want to do something else and some other computation is going on until the time this node sends back success or failure. In this case, you will use a stateful action node, which is again asynchronous. Let's make the constructor here. So this is our constructor. In my series on behavior trees, you must have seen that I was using 2 arguments, name and configuration. Here we are using node pointer as the 3rd argument for a reason. Since each behavior tree node is responsible to move the robot to a certain location, it needs this node pointer. That is because node pointer, which is your ROS2 node, is where you have access to your services and actions. We need an action to ask Nav2 to move the robot to a certain location. So you'll also save this node pointer. Here's an object for that. And as I said, we need to use actions inside this BT node. So we will have action client here. Now for a stateful action behavior tree node, we have to override these. So you have your provided ports. We will have an input port for each behavior tree node so that this node can get the location where the robot should go. You also have to override onStart, onRunning, and onHalted. We have used inline method here because this onHalted method will have nothing inside. If you are using RCL CPP node and action, you also need to include the right headers for that. So RCL CPP.hpp and RCL CPP_action.hpp. Since we have navigate to pose, we also need to include the right header for that. Whenever you use navigate to pose to ask Nav2 to move the robot to a certain location, it also uses a callback so that you know when that task is complete. So we will have this callback method, and inside this callback method, we will set a flag to true so that we know that this task is done. So you have your done flag. Now to make easy to code when we are writing definitions, this is what we add. These are essentially type defs and the scope is within the class. So instead of writing this, you will write navigate to pose when you're writing your definitions. We also need some more includes. You will know why I'm adding them when we write definitions for these methods. So you have your declaration. Let's start making the definition of your behavior tree node in your CPP file. You need to include the header file for navigation behaviors. Let's create boilerplate for all the methods we just wrote in our header file for navigation behaviors. We are using initializer list here for your constructor. Your node pointer is saved inside as a member, and this is what you need for your parent. This is the boilerplate for provided ports. This is for onStart. This is for onRunning. We don't need one for halted because that is inline. And the last one is your callback for Nav2 pose. So whenever you ask Nav2 to move the robot to a specific location, it will use this callback, and that is when we'll know that the result was successful or failed. Okay, so we have the boilerplate code. Now before populating this, we also need to make the design of the behavior tree in your XML file. So let's create a new directory called bt_xml. Inside your package, bt_xml directory. And let's create a file called tree.xml that will define your design for your behavior tree. And this is what your behavior tree's design is. It has one sequence node and 4 action nodes. Each node is responsible for one location and all of them take lock as the input port. So we can use this key. Now that we are here, let's also create a YAML file that will have 4 user defined locations. Let's create a new directory called config. Inside config, let's create a YAML file called simhouse locations. And these are the 4 locations in the world we actually saw in the previous video. Location 1, 2, 3, 4. So the robot will go to location 1, then 2, 3, and 4, and again 1, 2, 3, and 4. As long as the behavior tree is ticked and each action node is successful, the robot will keep moving from location 1 to 2 to 3 to 4 and so on and so forth. Now back to our CPP file for navigation behaviors. We have a behavior tree designed ready in our XML file. In the initialization of this node, we would actually need an action client instance. And done flag, which we declared in our header file, should be set to false here. Now, as I said, these 3 methods are overrides from your behavior tree.cpp node. If you don't know what I'm talking about right now, please check out my series on behavior trees and behavior tree.cpp. It'll help you understand all of this even in code, because I have the concepts in one video and also in 2 of those videos, I have code examples in C++. We have one port with the key lock that is defined in tree.xml. So this is your input port from which this action node will get the location of the robot to go to. Now we have a rough structure for this node. I could populate all of this with the core functionality right now, but just for you to understand it better, I will jump back to autonomy node right now. We will create a behavior tree here and tick it again and again, and then we go back to our core functionality and complete it. Let's first create a behavior tree. You need your behavior tree factory, of course. In the series I made on behavior tree, we used register node type to register nodes that had their own classes, but we cannot do that here. The problem is in behavior tree.cpp version 3, register node type can register nodes if those nodes have 2 arguments in their constructor. So if you look at your behavior tree node declaration again, you have 3 arguments in your constructor. This is what I'm talking about. We need the 3rd argument node pointer because this behavior tree node needs to access node and the client inside it to be able to ask Nav2 to send the robot to a certain location, right? There is another way to register a behavior tree node that takes in more than 2 arguments, namely name and config. To do that, instead of register node type, we do the following. Now, hear me out. What's happening here? On line 26, builder is the lambda function you need to create a node, a behavior tree node that takes in more than 2 arguments, not just name and config, but something more than that. In our case, we actually need to use the instance of this node itself. A small tutorial of this is already present in behavior.cpp official documentation. So please check that out for version 3. One small thing to note here is that we use equal to here because this lambda function needs to capture the external variable, which is the node. Now, once you've registered the node, you need to create the tree from your XML file. So here you have your tree created from your XML file. So create behavior tree is complete. You have your behavior tree created after this with 4 nodes. Each node is actually an instance of the class you created previously called goToPose in navigation behaviors. Now we said that this timer will take the behavior tree again and again at a set frequency of 500 milliseconds. It will call update behavior tree again and again for that, right? So we need to tick the behavior tree inside update behavior tree. This is how you tick the tree using tick root. You will get the status of your ticking here. For an asynchronous node, you can have either success, failure, or running. If there's a failure, it means that the behavior tree did not do what we wanted and there's a problem. If it's successful, then it is successful, your navigation is complete. And if it's running, then something is running, then the behavior tree is busy. So if your behavior tree is running, we just return and do nothing. If it's successful, it means you have finished navigation or at least one cycle of navigation is complete. If there's a failure, the navigation failed and we cancel the timer because something is already wrong. We don't want to take the behavior tree now since it already failed. Now we're using goToPose, which is a part of navigation behaviors. So to access this, we also need to include this. This is autonomy_node file. To do that, let's go to autonomy_node.h. Here we include navigation behaviors. Let's go back to your CPP file. This is autonomy_node.cpp. You need your behavior tree XML directory on line 34 to create your behavior tree from the XML file. To do that, we also need to access it. Now, to access it, we know that this is inside your package tb3_autonomy. You have your path, which is tb3_autonomy, wherever it is, then btxml and tree.xml. You know that you have tree.xml inside bt.xml, but we need the full path here, right? So you need path until bt underscore xml here. To do that, we can get the path of your package, and then we know that it is inside bt underscore xml. We can use something called get package shared directory. First, let's include that in our header file in autonomy node. This will be used to get the path of your package tb3 underscore autonomy. Let's go back to our cpp file. And this is how you get the path of your autonomy node, and your path of your bt underscore xml directory would be path of your autonomy node plus bt underscore xml. So now on line 37, bt underscore xml is something you can use using get package shared directory. Now we go back to navigation behaviors, but before that, we need to have access to your location file, which is inside config simhouse locations.yaml. We can of course hardcode that inside navigation behaviors.cpp, but let's pass it as a ROS2 parameter. And then if we say a ROS2 parameter, we also have to declare that parameter inside this node. Let's call this parameter location underscore file. So inside your constructor of your ROS2 node, you have your parameter called location underscore file with the default value of none. We will use this parameter inside your behavior tree node, which is go to pose, because that node has a handle on your ROS2 node. So let's go to navigation behaviors.cpp again. That is where your behavior tree node go to pose is. Okay, so the idea is your behavior tree will be ticked every 500 milliseconds once it is created. Each node will be ticked from left to right. It is a sequence node, and I hope you know what the sequence node is. The first action node needs to be successful for it to go to the second node, and then third and fourth. Again, if you don't understand this, please check out my series on behavior trees. Okay, when we tick the behavior tree using the timer inside ROS2 node, this behavior tree sequence node will in turn tick the first child node, which will be the leftmost action node. It will go to onStart of that node. We have our onStart method here. What do we want to do here? We want to ask Nav2 to move the robot to a certain location. For the leftmost node, it will be location 1. But since we are using the definition of your behavior tree node again and again, we need to get the location from the YAML file. How do we get the location from the YAML file? We first look at the port and get the value corresponding to lock. If you look at your XML file corresponding to lock, for the first node, you will have location 1. The second location 2, then location 3 and location 4. And in your simhouse locations, you have values corresponding to all of these, right? So you have location 1, 2, 3, 4. So that is what we do. We get a handle on the right string for that specific behavior tree node running, and we'll easily be able to get this. Let's go back to our behaviors. Here, first, let's get the key corresponding to your lock. So this will get you the value corresponding to the key lock in your tree.xml file. So this could be location 1, location 2, location 3, or location 4. Now, once we have this, we can also read a YAML file. But as I said before, the path to that YAML file is passed as a ROS2 parameter. Since we have a handle on a ROS2 node here, we can easily get that parameter value. That parameter value will be location of the file. So we'll have our location file as string, and that is why we included string. Now it is a YAML file, and once you have a path to the YAML file, you can use your YAML library to read that file. This is how you read your YAML file, and that is why we included YAML CPP. Let's read the right value as a vector. So we'll create a vector called pose that will have the right location of where the robot should go to for this specific behavior tree node. Log.value will give you location 1, 2, 3, or 4 in string. And if you go to locations in simhouse locations.yaml, you will have the right list, or in this case, the right vector. So we will read the right vector. It could be either this or the second one, third one, or the fourth one. Okay. So you will have your pose here as a vector. So now we have the destination pose of the robot where it should go to for this specific behavior tree node. We should now send this as a request to Nav2 using an action client. We already have an action client here, right? This is your action client. So we will need to create a goal. Let's create your action client goal. You need your goal options for Nav2. And we'll set our callback for this goal, which will be nav2 pose callback. We of course have to use std bind. If you don't know what std bind is, I have a video on that. Please check that out. Now we have set our callback in send goal options. So now we can actually make the pose and send a request using this action client. Since we have the locations from our YAML file, let's make the pose. This is the message we want to send. The first thing is setting the reference frame. This will be with respect to map, X location, and Y location of the robot. Now the third one is your angle in theta, that is here. This is your theta, but we need to transform that to quaternion for us to send this as a request. And that's why we had to include quaternions. We use quaternion from TF2. We set roll pitch yaw using the third value in our vector. We normalize this value because theta is transformed to quaternion. That will be x, y, z and w. And x square plus y square plus z square plus w square should be 1. And that is how we do it. Now we have a quaternion value. Let's write it to our goal message. We are now ready to send this as a request to Nav2. This is how we send our asynchronous request. Let's also have a logging statement here. Now, since this behavior tree node will be busy until Nav2 says it succeeded or it failed, which will happen using this callback, this behavior tree will be busy. So we return this value running for this node, which means that this node is busy and in turn the behavior tree is busy. Well, we also set done flag to false here because when you're sending a request, it means it is not complete, of course, right? So we start with false and we'll set it to true here if the result says it is successful. Now what happens with on running? Every time this node is ticked, but it is already running, so it is busy because the robot is actually moving to the goal position, but it is not done. We do nothing. We just send back running status. But also if it is running and Nav2 already said that, hey, I'm done with my job, we can say that the result is successful for this. So this will send back a success. So if done flag is true, which is something we'll set here, we send back success, which says that this node's job is successful. But if done flag is false, we send back running saying the node is busy and the robot is actually on its way. And here Nav2 post callback will be used when Nav2 says that it's done or it failed. So you'll have result, and inside this you'll have an empty signal. Nav2 sends back an empty signal, which means that the navigation is actually completed. So you'll set your done flag to true, and this is how your code is set up for your core functionality of your behavior tree. Okay, so we are done with the code. We need to update our CMake lists and package.xml. Let's start with package.xml to include all the dependencies we have. When we created this package, we only used RCL-CPP as the dependency, but we have the following dependencies here. We are using all of this, right? We are using RCL-CPP action, Nav2 messages, behavior tree CPP version 3. I am using version 3, YAML CPP, TF2 and TF2 geometry messages. This also needs to be reflected in your CMake lists file, of course. Let's save this and go to CMake lists. Let's start adding all the packages we need first. Apart from RCL-CPP, we need to add all the packages we just added in package.xml. So RCL-CPP actions, Nav2 messages, behavior tree CPP version 3, YAML CPP, TF2, and TF2 geometry messages. Now we have bt_xml and config directories for supporting files, so to speak. So let's add them. We need to install these directories. Let's set a variable. We set a variable called behavior tree sources that will be used when we add our executable some lines below. And we set our target dependencies. This is the same list as the one we see above. Since we're using include files, we include directories, which is for autonomy_node.h and navigation_behaviors.h. We need to add these 3 lines now. Add executable will add the executable for your ROS2 node, which will be in autonomy_node.cpp. It also uses behavior sources, which is your navigation behaviors.cpp, and that's why we have it here. In target dependencies, you need all these target dependencies. And target link libraries is for YAML CPP library. Now this is not, of course, defined here. When you actually use YAML CPP, one of the files there, one of the CMake files will have the value set for YAML CPP library. So that's why it works here, but you need to link that library separately. That's why we need to have target link library for YAML CPP. Now you need to install your autonomy node target. We add that for adding your autonomy node target. So we have our CMake lists and package.xml also ready. One last thing we need to do is create a launch file to actually run this node. Let's create a launch directory. Inside the launch directory, let's create a file called autonomy.launch.py. Since we have spent significant time writing launch files in the previous video, I won't go into the details of this, but let's only look at the main part, which is autonomy node. This is where you get your autonomy node from. If you remember, I said that we will pass the location of the file simhouselocations.yaml as a parameter to this node, which is in turn used by the behavior tree node go_to_pose. You see this parameter has the key location_file, and this is your full path of your file simhouselocations.yaml. We use package for tb3 autonomy, which will give you the path for tb3 autonomy. we use it from here. Again, get package share directory. That's something we also use in the CPP file for some other reason. That was for getting your bt_xml file from code. But this is getting your package share directory so that we can use the location of the file. So effectively they're the same use cases. It's just that one is used in your CPP file. The other one is used in your Python launch file. So this will create your launch file for your autonomy node. I think everything should work. If there's an issue during build, we'll see that. Let's build the project. Let's go to your workspace and let's build this entire workspace. So there is a failure. Let's see what is wrong. Okay, we do not have a semicolon here. Okay, so we do not have a semicolon here, and it's also there in this file below for setup. Okay, let's build this again. Okay, so 18 packages finished. Everything is finished. Now let's see if we have a project where you have a robot in a world, navigation 2 is up and running, and from our application layer, from our code, which will have all the computation for a real project, we're able to move the robot to location 1, 2, 3, and 4, and so on and so forth using an external behavior tree we just created in C++. To do that, let's clear this. In the previous video, we needed two terminals, one for launching your world in Gazebo with the robot, of course, and the second one was for launching your Nav2 infrastructure. In this video, we'll need three. One for, of course, your Gazebo simulation, the second one for your Nav2 infrastructure, and the third one will be to run the node we just created, which will be autonomy node. Let's have a clean screen right now, and we'll start with the first one, which is for your TurtleBot 3 simulation in the world. I'll source my ROS workspace. Before I run any simulation, I need to export Gazebo models for TurtleBot. So I do that. I'll use wafflepie. Let's launch the simulation. TurtleBot3.world.launch. So using TurtleBot3_world launch file, we have a simulation ready. What was the second component? As per the previous video, we had our Nav2 infrastructure set up, which was also a part of your TB3 sim. So in a new terminal, source workspace again. Let's launch your Nav2 infra. So your Nav2 infra with RViz and AMCL init post done is also up. The third thing you have to do is launch your autonomy node, which will ask the robot to move to position 1 or location 1, then location 2, 3, and 4. Let's source in another terminal. Let's launch our autonomy node using the launch file. Inside a package tb3_autonomy. The launch file is called autonomy.launch.py. Let's see what happens. So your robot is moving from location 1 to 2 to 3 to 4 and so on and so forth. One thing for you to note is that I am right now using Humble. In Humble, there are times when I have to run this node, autonomy node, again and again. I built all of this in Galactic and it was seamless. But when I'm using Humble, I sometimes have to launch the node. It doesn't work and then launch it again. That is something I'm looking into, but it's definitely not an issue with the code because it was perfect when it comes to Galactic. But the idea is, using this application code or this application package, we ask the robot to move to 4 different locations in our world. And that is the entire project of creating a Nav2 patrolling robot in ROS2. As a recap, we started with creating a simulation in the world. We then added our Nav2 launch files so that Nav2 can start and all the infrastructure for Nav2 is complete. After that, in this video, we created an application layer, which is supposed to be the main place for our application to run. In a real scenario, it would have all the compute. Let's say you have a vision module. The vision module will be able to decide where the robot should go to. And then using that, you would be able to ask Nav2 to move the robot to a certain location. So this was the project about a patrolling robot in Nav2. With this, we conclude this project, and I hope to see you in the next videos and in the next series as well. Thank you and have a great day. Bye-bye.